Hello there. I'm going to just run through some quick math examples for basic linear motion in physics. And keep in mind that for all of the situations that we're currently going to be looking at, we are going to ignore any type of air resistance or friction. So the first thing we want to do is we want to go through and look at what are the most common variables that we're going to be working with, because we have to understand the notation in order to understand our formulas. So the first one we have here is a lowercase t generally represents time. Majority of the time it's going to be measured in seconds, but that's not a requirement. D we are going to let stand for distance. Most of the time we'll be working with meters, but it could also be any other form of distance. V sub 0, that's going to represent our initial velocity. And by initial, that means the starting velocity. Now if an object is just dropped, then its initial velocity is 0. V sub f, that represents our final velocity. Now that doesn't necessarily mean the velocity at the end of motion. It means the velocity at the end of whatever our problem is referencing. So if we're looking at an object that's moving for 3 seconds, our final velocity for that particular problem would be the velocity that's occurring at 3 seconds. V with a bar above it, that is our average velocity. And the triangle here, that is the Greek letter delta. Delta represents change in change. So when we have delta V, that represents our change in velocity. So how much has our velocity changed? And then A, we use to represent our acceleration, or how quickly is our velocity changing. When we're dealing with problems that involve gravity, sometimes you'll see G in place of A. So if you see G, that represents the acceleration due to gravity. So it's still our acceleration. Now we're going to look at where some of these formulas come from to start with, and then we'll get into the problems. So let's say that we have a situation where we have an object that at time 0, our velocity is 0. So we're starting from rest. And then we're also going to assume that it's going to accelerate at 2 meters per second every second. So what that means is that after 1 second of time, my velocity is going to have increased by 2 meters per second. So I was currently at 0 meters per second, increased by 2 meters per second, and that would put me at 2 meters per second. Then when another second passes, I'm going to increase 2 meters per second again. So I would now be at 4 meters per second. And then when another second passes, I would increase 2 more meters per second. And then when another second passes, I would increase 2 more meters per second. So the first formula that I want to look at is delta V. Now to represent our change in velocity, if I'm looking at this particular time interval from 0 to 4 seconds, I can compute my change in velocity by looking at where I started and where I ended. Well, to get my change in velocity, I would take my final velocity of 8, and I would subtract it from my initial velocity of 0, and I would end up with a change in velocity of 8 meters per second. And I got that just by looking at my table. Now, this leads us to kind of our first variation, I guess, of this formula, is that our change in velocity can be computed by taking our final velocity, so V sub f, minus our initial velocity, V sub 0. Okay. Now, we can also find our change in velocity slightly differently. So if I know that my acceleration was 2 meters per second and my time was 4 seconds, I can come up with that 8 meters per second by taking my acceleration times my time. So if I took my 2 meters per second squared, because it's an acceleration, times the amount of time, well, it was moving for 4 seconds, I will end up also with 8 meters per second. Now my units here, since I have meters over seconds squared for my acceleration and I'm multiplying it by seconds, these will cancel out and just leave me with meters per second, which is what I needed. So I have another formula that I can use to find my change in velocity, and that's when I take the acceleration times the amount of time that it has occurred. So we will write that as delta V equals AT. Now this would work no matter what our starting velocity is. So let's say instead of starting at 0, let's say our starting velocity had been 7 meters per second. And I'm still going to be accelerating at 2 meters per second. So after my first second, I would be up to 9 meters per second. And then after one more second, I would be at 11 meters per second, and then 13, and then 15. Well, if I want to find my change in velocity, I started at 7, went to 15. Well, if I use my first formula here, where I take my final velocity minus my initial velocity, 15 meters per second minus 7 meters per second, I still get the 8 meters per second that I got before. And if I use my second formula here, my acceleration was still 2, just like it was right here, and my time didn't change at all, still 4, so I end up with 8 meters per second again. So it doesn't matter what your velocity is starting at. These two formulas right here for change in velocity will work no matter what. Keep in mind, we are still assuming that we have no friction, no air resistance, and we're also assuming that we have constant acceleration for these types of problems. Okay. Now, let's say I wanted to find my final velocity. So we're going to use this second data set there. Well, my final velocity was 15. And I knew that I started at 7 meters per second and I changed by 8 meters per second. So when we came up with the 15, we can rearrange this formula here. Add 7 meters per second to both sides. Now I'm not actually going to add those together. I'm just going to leave it as 8 meters per second plus 7 meters per second for the time being, because we want to have those components. Now this 7 meters per second, that was my starting velocity. Okay, that's my initial velocity. And this 8 meters per second came from my change in velocity. So I could put delta V there. So this 15 meters per second that we had, we could have found that by taking our change in velocity plus our initial velocity. Oops, I didn't want 15 there. I wanted final velocity there. So that is one way that we can also find our final velocity. Now we can modify this slightly. We can put down that our final velocity, instead of delta V, we could substitute VF minus V minus the initial velocity in there. Not going to help us out most of the time. Or we can substitute the second equation in there, where I can put acceleration times time plus my initial velocity. So this is just an example to show you where some of our formulas that we're going to look at on the next slide come from. So for this course, most of the formulas that we're going to be using at this particular point in time are going to be just kind of our basic ones. Now the numbers I have over here, that is just so I can reference the formulas for this video. Okay, those are not universal numbers for anything. So our first formula is to find acceleration. If it's not given to us in the problem, it's just our change in velocity over our change in time. Okay, the second one that I have listed was what we just derived on the screen before this. My change in velocity, I can either find that by taking final velocity minus the initial velocity, or I can find it by taking the acceleration times the time. Okay, and then my third formula is also one of the formulas we just looked at. I can find my final velocity by taking my initial velocity plus the acceleration times time. Okay, my fourth formula. This symbol right here, that was our symbol for average velocity. And if we assume that we have a constant acceleration, to find our average velocity, we can take our initial velocity plus our final velocity, so add those two together, and then take that answer divided by 2. So it's finding just the common average of your starting value and your ending value to get your average velocity. Now keep in mind though, that is only for constant acceleration. Okay, and then the fifth formula that we have on our list is distance is equal to our average velocity times our time. So if you think about driving in a car and you are driving at an average rate of 50 kilometers per hour and you travel for 2 hours, well, your distance you covered in that 2 hours would be 100 kilometers, because you would take your 50, your rate, times the amount of time that you were going. Okay, and then our last formula for this particular video is distance is equal to 1/2 acceleration times your time squared. Now this one's a little bit harder to derive for a basic physics course, but it's a very, very useful formula because it is one of the formulas that we have that will relate distance to our acceleration. All right, so we are going to primarily focus on objects that are in free fall or objects that are being thrown, usually upward, but they can be thrown downward. Some things to keep in mind. Even though it might not be explicitly stated, if it is in free fall, then we have acceleration due to gravity. And if you are here on Earth, the acceleration due to gravity is approximately 9.8 meters per second squared. And sometimes we will just use 10 meters per second squared because it makes our computations easier. So if you need to have a very accurate answer, then you would use 9.8. If we're just trying to get approximations, we would use 10 meters per second squared. Okay? If the problem states that an object is dropped, that implies that our initial velocity is 0. Okay? So it might not explicitly state that the initial velocity is 0, but if you see that it's being dropped, we know its initial velocity is 0. If we have an object that is thrown with an initial velocity, or if we have an object that is thrown, it has some initial velocity other than 0. Now, depending on the problem, the item could be thrown upward or the item could be thrown downward. Okay? So then we would have a velocity, an initial velocity other than 0. Okay, and then our fourth one is that if an object is thrown upward, it's usually easiest to do these types of computation problems by separating the motion into 2 halves. Okay, motion on the way up and the motion on the way down. The reason for that is because we know that the velocity at the very top of the motion is equal to 0. So that instant when the ball or the rock or whatever is being thrown is at the very top of its motion, its velocity is 0. That will help us. So if it was going up, right before it starts to fall back down, we have that spot where we know its velocity to be 0. Okay, and then the second thing that is very helpful is that the amount of time that it takes to go up is equal to the amount of time that it takes to go down.